Morning. Good 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 morning.
Why don't we just come up here? I know, when you like, yeah, when I looked at him.
Good morning. 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 Wow. Attendance is not overwhelming, but I'm very glad that you're here. Thank you. Good man. Quickly need to check something. Good. We are in business.
random, but it works for me in my brain. I see. Well, I'm not going to tell that story to my kids, put it that way.
Morning.
I know they'd be on something.
It's week 32.
It is week 32.
Sorry, you're what?
Week 32.
Week 32. Yes. We've got, well, after this week, it's only 3 weeks left. Scary.
And yeah.
And then exams.
So I could show you.
Good morning. Good morning. Okay, let's make a start. Most wonderful good morning, everybody. And welcome to continuation of our little tour through data analysis and statistics. I was told that the code works, so please do register your attendance. And in this session, the plan is to expand on what I showed you last week, what I started last week, which is basically we started with the topic of hypothesis testing, where we said when we want to do some tests, statistical tests, whatever form or shape they might be, we have a sort of a set of rules. And I really want you to learn these rules because it makes life so much easier for you guys when you do data analysis. So we started off, and last week I gave you these rules. And what I want to do today is really want to apply these rules and show you how we can actually work with these things to get some meaningful results. So, for example, we said we need to formulate a null and an alternative hypothesis. That is step one. That is, we always start with that. So the null hypothesis would be, for example, that we say there is no difference between the two population means. Remember, we can't compare the samples directly because of sampling error, but we can sort of think about from what population do these samples come from, and therefore we can compare the populations from which we have the samples. And we can formulate that. We can say any differences between the two samples can be explained by sampling error. Then we can formulate the alternative hypothesis, and I have put down one alternative hypothesis, and today we will see also a different alternative hypothesis. So here in this case, we just negate and do the opposite of the null hypothesis and say there is a difference between the population means, and the differences between the samples are due to sampling error and an additional effect. Probably that what we are investigating, whether it's a drug or treatment or something like that. So that is the step one. Step two, we set the significance level. That is basically the level that we are willing to make a type 1 error. And I explained in the last session what a type 1 error is, that the bouncer basically rejects something that they should not have rejected. So that is the type 1 error. We then formulate decision rules, and we say we make a decision based on what we are going to calculate. calculate the probability, and if this probability is lower than our significance level, we just simply say, yes, we can reject the null hypothesis. If the p-value is larger than the significance level, we fail to reject the null hypothesis. And we will do that exactly today. We then, of course, have to calculate this p-value. And step 1, 2, 3, that is the stuff that you do before you start any calculations, right? This is what you set out before you get started, before you get the calculator out. And that's really important. In step 4, we calculate a test score. And I will show you how we do that today. And we then say, how likely is it to find this test score if we assume that the null hypothesis is correct? And in the last step, we then go back to number 3 and say, okay, we've got this p-value, we compare it with the alpha, and we go back to our decision rules and make a decision. Does the drug work? Yes or no? And that is basically outcome. And that is really formulaic process that we are going to use every time we do a statistical test. And it doesn't depend really on the statistical test. We might need to reword the null and alternative hypothesis a little bit, but the steps in principle are exactly the same. Yeah. So that's where we sort of left last week. And I also showed you last week that we could, for example, have a drug treatment where we look at the size of a tumor. We have 8 people who did not get the drug, and we have 10 people who got the drug. And we wait for the drug, and we then measure the diameter of the tumor. So this is our data set that we obtain in, say, a clinical trial or clinical study or something like that. And what we can do now with that is we can do a little bit of sort of statistics. We can calculate the mean for each. So we have 58.2 micrometer in the cohort without drug and 33.7 in the cohort with drug. We can calculate the standard deviation. We note that the standard deviations are quite different from each other. Yeah, so that's sort of just as a sort of a side note. Bear that in mind. We have the sample sizes, N8 and N equals 10. That's just simply how many participants we have in that study. We can also calculate the standard error. And I showed you previously how we calculate the standard error. That is just simply the standard deviation divided by square root n. Yeah, and we can do that. And in the case of without the drug, we have a standard error of 9.9. And in the case of the situation with the drug, we have a standard error of 3.7. So the standard errors are quite different from each other, but not by orders of magnitude different. So they're sort of in the same ballpark figure, which is quite nice. Okay, so how do we find out whether the drug works or not? We can probably already have a sort of a gut feeling. The sample means look different. Maybe this is because the drug works, but we can't be sure. It could still be sampling error. So what we are going to do, please don't forget to register your attendance. We are just simply formulating, we are starting with our hypothesis testing, right? So formulate the null hypothesis. And what you see is I just simply copied the step that we set. There's no difference between the two population means. Any difference between two samples can be explained by the sampling error only. So we can write the population mean with the drug or without the drug equals population mean with the drug. So without equals with drug population. Yeah, that is mathematically how we can write this null hypothesis. Mu1 equals mu2. Now, mu1, H1, our alternative hypothesis. I told you we can write that in different ways, and it has then different implications. So the most common one, and I want to encourage you to use the most common one, is where we say there is no difference between the null hypothesis, there's no difference, and the alternative means there is a difference. So we would write this as mu1 is not equal to mu2. What does that mean? It can mean mu1 is smaller than mu2, or it can mean mu1 is larger than mu2. It can mean both. It just indicates it's not the same. Yeah. So we have two options here. Mu1 is smaller or mu1 is larger. And because we've got two options, the test that we are going to do is what is called a two-tailed test. Of course, we could also say, well, we are predominantly interested in whether mu1 is smaller than mu2. Anything else is not of interest. So we have only one option here. So that would be a one-tailed test. Because we only say we are interested in, is it smaller? Anything else is of no interest. Two-tailed test says it's different. And I encourage you, wherever possible, always go for a two-tailed test. Yeah, always go two-tailed. Okay, so we've set that up, our null hypothesis. Next one is set the significance level alpha. What is our willingness to commit a type 1 error? And I would just simply say, let's set this to 5% or 0.05. That is standard. Yeah. Next, formulate the decision rule. And, you know, again, it is incredibly boring. This, if P is lower than alpha, if P is low, H0 must go. And we are happy with our alternative hypothesis. Okay? If P is larger than alpha, we say we fail to reject the null hypothesis. As I told you, we are not accepting it. We just simply say we fail to reject it. Okay, so that's our decision rule. And now we need to calculate or find the probability for the test score. Now, in our case, we are working with continuous data because the size of the tumor is sort of, you know, a continuous number. And it would be appropriate to use what is called a student t-test. And I just simply can't resist the temptation to tell you a little bit about the history of the student t-test. The student t-test was invented by a brilliant mathematician in, I think, around the 1900s. There is a link to Canterbury because this person by the name of William Gossett was actually born in Canterbury. I think he went to King's School and then did a PhD in Cambridge. And after his PhD in maths and applied maths, he got the dream job. He was employed by the Guinness Brewery in Dublin to work for them in the quality assurance department, because the owners of the brewery were very concerned that, you know, sometimes the different batches that they produce tasted a little bit different and had different alcohol percentage proofs and things like that. So they said, we want a way to ensure that everything that we produce is basically the same. But how do we do that? Before they hired Gossett, I heard rumors that on a Friday afternoon, the workers had to test the different batches of Guinness that were produced during the week and sort of score them. You can imagine if they started in the morning drinking Guinness, then the rest of the day was probably not as productive as they would have liked it. So they thought, no, that's not a good idea. And so they employed Gossett to come up with a sort of a method, actually, that allows them to really measure and compare samples. Are these samples consistent? Do they all have the same requirements, or are they from vastly different populations? And Gossett came up with what he called a test. That's the T, test, just simply. He was not very imaginative. And came up with this test thing, with this T test, as it was called then. And the owners of the brewery were incredibly happy with him. And he said, can I publish it in a scientific journal? And unfortunately, the Guinness brewery company had a very strict rule on publications. They said, yes, you can publish it, but there are a few conditions. Firstly, you must not name the company, because that's all commercially sensitive. Yeah, you must not name the company, and you must not write under your name. So you have to use a pseudonym, and you cannot be identified a link with the company. So Gossett then thought, okay, I need to give myself a different name. What name shall I give myself? I'm not terribly creative. And he came across a little notebook where he took his notes, and the notebook had written on it, student notebook. And therefore he thought, okay, since I am continuously still learning, I think of myself as a student, and therefore he published the work under the name student. And that's why this test is called the student t-test, right? Okay, so how does it work? Well, actually, there is a calculation that calculates this, what is called a test score, the t-score. You can write that down, but we will come in about 5 minutes. There will be a caveat, right? And I do not want you to, well, I'll tell you later. The t-score is basically sample 1 minus sample 2. the means divided by the square root of the standard error of sample 1 squared plus standard error sample 2 squared. That is the t-score. Okay? At least that is the t-score that Gossett used. And what you would then do is you just simply get this t-score. You use a t-distribution. Let's say here's our t-score. And we measure what is the probability of getting this t-score or a higher value. So basically, what is the probability to get this bit here? Yeah, that is the principle. And that gives us this probability, that gives us this p-value. Now, when you did that at school, you probably had to look. Did anyone do that at school, p-values?
I think we did something. We did that in college.
Yes, you probably did that with tables or something like that, where you had to look up a p-value. Or, yeah, you did that, yeah. Okay, breathe easy. We have arrived in the 21st century. We are not working with tables, right? But let's say we get a p-value for that. And what we now need to do from this procedure, take this p-value and compare it with our significance level alpha. How would we get the t-score? How would we get the p-value? Okay, I probably have alluded to it already. This is the equation that you have here. And please never, ever use this equation. I'm just putting it up here because you need to know about it, but don't use it. This is the equation for the classic t-test. But the classic t-test is only valid if N1, the sample size of sample 1, equals the sample size of sample 2. And S1 is pretty similar to S2. The standard deviation of sample 1 is similar to standard deviation of sample 2. Now, I showed you, in our case, we don't have that. Our sample sizes are different, and S1 and S2 are different. And if you use a t-test with that, it will give you some numbers, but these numbers are meaningless. Yeah. Now, 50 years later, after Gossett, a very clever person by the name of Welch came up with a modification, and that is actually a t-test. And I don't show you the equation for it because you start hyperventilating when you see this equation. It's a little bit, not terribly user-friendly. This Welch test actually works if the sample sizes are not the same, if the standard deviations are not the same. So how do we deal with that? Well, the good thing is there is an online calculator which you can use. I very strongly, and I will send out a link to this online calculator, I very strongly recommend that you not only scan this thing, but also that you bookmark it, because you will need it for assessments. And I swear to dog that this is the single most useful tool that you come across apart from my wonderful website. But this is an excellent online calculator. Yeah, please. And we will use that in lectures to come. You can also use Excel, believe it or not, for what is known as this Welch test. Yeah? And the equation for that is just simply equals t dot test, the array of sample 1, the array of sample 2, and then you have to put in a number 2. 2 stands for two-tailed test. And the last one is number 3, which stands for Welch test. If you put in number 2, it will do the traditional t-test, and it's just nonsense. So go for 3. That will give you the t-test. Now, when you put these data into this online calculator, I think I've got a screenshot. Yep, you get a beautiful screenshot. So here on the left-hand side, you've got sample 1. You've got sample 2 on the right-hand side. Yeah. Shows you the distribution. It shows you even, which is incredibly useful, the margin of error. For both samples, that is this plus minus. It tells you the lower confidence interval and the upper bound of the confidence interval. Yeah, you don't even have to calculate anything. How cool is that? Yeah, fantastic. And even better, it calculates automatically for you the p-value. That is the probability to find this t-score. Welch test also uses a t-score. And here the t-score is 0.046. So we calculated the p-value. P equals 0.046. And now we go back to 0.5 and say 0.046 is smaller than our alpha, 0.05. Yeah, definitely smaller. Let's see what we said. We said if p-value is smaller than alpha, we reject the null hypothesis and are happy with the alternative hypothesis. What was the alternative hypothesis? We said there is a difference between the two populations. We can't explain this difference by just simply sampling error. Yeah. So our conclusion is drug works. Hey, cool. Important. Some people say, oh, the p-value is very close to alpha. So 0.046 is not too far away from 0.05. So maybe not really close, maybe it doesn't really work. No, the p-value and how close it is to alpha has, in this case, has absolutely no meaning how close it is. It is just simply a decision tool. Is it smaller than alpha? We reject. If it is larger than alpha, we fail to reject. If the p-value is, for example, 0.05001, tiny little bit larger, doesn't matter whether it's tiny little bit or huge, it is decision, we reject. We fail to reject, sorry, because it's larger. Yeah? Says nothing about how close things are, how good the drug is. It is a decision tool. It is just simply a decision tool. That is the definition of the p-value. It is a little bit, let me compare that quickly to a pregnancy test. Yeah? A pregnancy test tells you you are pregnant or you're not pregnant. It doesn't tell you how much pregnant you are. Right? That is the definition of a p-value. Happy with that?
Well, but p-value is a continuous number.
P-value is a continuous number, yes.
Yes, so why cannot be used as a spectrum?
Because the p-value, sorry, because I didn't get the last bit. Why don't we use the? Repeat your question, please. Sorry.
But p-value is not just a Boolean, true or false. It is a continuous number.
Yes.
So why cannot we use it as a spectrum?
Because there are a number of reasons for that. One of that is related to the sample size. Don't want to go into it. Just simply believe me, you can't make a judgment how big sort of the effect is of the drug. It is just simply, does it work, yes or no? Yeah. This was actually what is known as a two-sample, two-tailed, independent t-test. Sometimes you see it also Welch correction or Welch test. Independent means the samples are absolutely independent of each other. Two-sample, two-tailed, because of the alternative hypothesis, independent samples are not related in any way to each other. Very common that you will use that. Yeah? It is a decision tool. Does the drug work or not? Yes or yes. Excellent. Now, let's assume we want to investigate only one sample. So we would have one sample, two-tailed, independent, t-test. And we would have this when we are looking at, say, tumor size, and we know already that the typical tumor in the population would be around 50 micrometers. So we don't have a second sample, but we know that the typical tumor is 50 micrometer. So what we are basically asking is there a difference between the population mean from our sample and the reference value?
About the high-squared test.
No. And the reference value. It is still a t-test. The calculation is in principle exactly the same, only that instead of, when I said we have this x1, x2 over square root SE12 plus SE2 squared, this one here is now our reference value. And we don't have this one here, the standard error for the reference value, so we don't have that. So in a way, this one sample t-test is easier because we are just dealing with one sample. And we can try and figure out what is the probability to find this t-score. Again, we need to sort of think about how do we do that. And in the online calculator, it's very simple. You can't do it in Excel, by the way. Oh, yeah, you can do it in Excel, but it's a little bit, you have to work around. In the online calculator, we just simply do the following. We just enter our data for sample 1. That's sample 1. And for our sample 2, our reference value, we just put in twice the reference value. Yeah? Twice the reference value, that will do. And now we ask, is the reference value different from the population mean from our sample here? And what we just simply do is we look at the p-value that we get. We get a nice p-value, 0.44. And as Irina absolutely correctly says, p is larger. So p, let me write this down. P equals 0.44, which is larger than alpha. Our conclusion is fail to reject the null hypothesis. This means although our sample mean was 58 micrometer, it is perfectly in line with the reference value of 50 micrometer. Yeah?
But since we failed to reject.
The null hypothesis is there is no difference between reference and population. So we fail to reject. Yeah? Make sense? Good. Excellent. So that is a one sample, two-tailed, independent t-test. Brilliant. Now, of course, what we could do is another test. We could say we had patients, say we take 8 patients, we measure for each patient, we measure the tumor size before the drug treatment, and then we give the drug, wait a little bit, and then measure for the same patient. It's the same patient, right? After the drug, the tumor size. So what we have here is basically a list with the patient number. So patient 1, before the drug had 64.2 micrometer, after the drug had 45 micrometer. So the tumor obviously caused a difference here of 19.2 micrometer. That is due to drug. Now, what we have here is undoubtedly 2 samples. We will perform a two-tailed test. But now the data are no longer independent because this where am I? Oops. This number here is linked to this number here. This number here, 83.1, is linked to this number here. So they are no longer independent from each other. Yeah? Makes sense? So therefore, this test is not an independent t-test. It is actually called a dependent. You also find the expression a paired because you've got 2 pairs. You've got pairs. Yeah? Or it's also called a matched t-test. So how do we deal with that? The answer is simple. In Excel, we can do equals t-test sample 1 sample 2. We still do a two-tailed test, so we have the 2 here. But instead of the independent Welch test, you put in the number 1. This means paired or matched or independent. And it will do the calculation. What does it do? Actually, what it does, and that's why the number 1 is there, it converts this to saying, we've got the difference here. So test the difference. We basically test the mean of the differences test the mean of the difference. So we calculate the mean here. Let's call it x bar mean, x bar d difference. And we ask, is this different? Is it different to the reference value equals 0? So here we have another reference value, and we set this reference value to 0, which means there's no difference. Yeah? So the reference value is 0. So what we could do is we could just simply use these numbers that we just calculated, the differences, put that in our online calculator, just copy paste, and on the right-hand side here, we would just simply put in 0. And that would give us a p-value. And with this p-value, we just simply say, right, p-value larger than alpha, we fail to reject, or p-value smaller than alpha, we reject the null hypothesis. So this is actually how we would deal with, is it? Where have I put that down? Have I missed that? I thought I've just put that somewhere. No, apparently not. So we have two sample, I've written it down, two sample matched or paired t-test. These are 3 t-tests that you will commonly encounter. The 2-sample independent t-test, which you can do very easily in Excel. The 1-sample t-test that compares a sample with a reference. That's the 1-sample t-test. And a special form of the 1-sample t-test is the 2-sample paired or dependent t-test, because in this latter case, we just simply set the reference value to 0. Probably need to do a little bit of exercises, but there are exercises on my wonderful website. And we will go through a few more examples in the next session. Happy with that? Yes, Irina.
What is the difference between p-value and t-score?
Okay, the t-score is a number, and the p-value tells you what is the probability to get this number if we assume that the null hypothesis is correct. The t-score can be any number from -infinity to +infinity. The p-value is the probability, so it can only be between 0 and 1.
Okay.
Make sense?